a note on the exam. That was distressing to me that the average turned out to be 66. And there are 0 scores in the 60s. So people either above or below, but nothing in the middle. That's a really bimodal distribution here in statistics terms. That's distressing to me. If you find yourself in this bottom group, I want to talk to you. Please come talk to me about what happened on this exam and how I can help. No one is in a position where they cannot dig themselves out. We have 2 more exams, another 15 homework assignments. We got plenty of stuff still to get grades in, but that's a substantial shift with that big break in the middle. I find that a little distressing, especially because the exam was doable. Okay. The rest of today's discussion will be fairly theoretical. Both Rolle's theorem and the mean value theorem are based off of the ideas of what it means to be continuous and differentiable, and what effects this has on things like our extreme values. So let me start with Rolle's theorem. Let's suppose I have a function that satisfies the following 3 properties. It's continuous between A and B and at each endpoint. It's got a derivative on that same, well, maybe not at the endpoints, but on that same interval. Everywhere between A and B, we have a derivative. And the 2 endpoints have the same y values. Now, before I go any further, I'd like you to draw a picture that satisfies these conditions. What graph can you make? It's going to satisfy all 3 of these rules. Well, I know I need an interval from A to B. So let me start with 2 numbers on the x-axis, A and B. They're going to have the same y value. So whatever this y value is, it's the same there as it is here. And the only thing I know about the graph between these 2 dots is that it is continuous and differentiable. I want you to draw me a picture. Play connect the dots. You need to draw a function, so you can't go back and forth from left to right because you need to pass the vertical line test. I want you to draw me a continuous function. You can't lift your pencils. No holes, no jumps, no gaps, no vertical asymptotes. I want you to draw me a differentiable function. No vertical tangent lines, no sharp corners, no cusps. Draw any curve you want connecting those 2 dots. Dean, as I'm going from A to B, do I go up, down, or straight across first? Yeah, you're drawing the air in front of you. What are you going to draw when you connect these two dots?
Down, up, up, down, to it.
Perfect. You could draw anything. You could just go down and then up and hit. You could go up and then down and hit. You could go straight across. Doesn't matter to me at all. As long as you draw a function that hits all three of these properties. Here's the consequence. On this function, I want you to draw a tangent line. I don't want you to draw just any tangent line. I want you to draw a tangent line that's horizontal. I guarantee you, no matter what picture you drew, it doesn't have to look like the one Dean just narrated to me. If you draw a picture, there must be a spot somewhere on the picture you drew that has a horizontal tangent line. In this case, there are two of them. Somewhere around here and somewhere around here. No matter what picture you draw, there must be a spot somewhere between A and B that has a horizontal tangent line. On page 290, here are several other versions of this picture. If you went straight across, then every single point will have a horizontal tangent line. If you go up and then down, there'll be some sort of a maximum. Since my function has a derivative and has a maximum, Fermat's theorem tells me the derivative must be zero there. Same thing here. This is kind of the backwards version of the one we just drew. Here's one that goes down and then up. There must be a place with a horizontal tangent line. The only way you can avoid this, if you start to go up, but you don't want to turn to come back down, you have to lift your pencil, right? You just made it not continuous. Or you have to make a sharp corner so that you don't turn over. And that's failing to be differentiable. If I'm insisting on derivatives and insisting on continuity, I must have a flat spot. Does this make sense? Some of you are staring at me like I've just spoken in Farsi. I can do it in Spanish. ¿Está comprendo? Does this make sense? Okay. So, in what? What does this do for me? What possible benefit is it to have this? Well, calculus is, in a sense, an extension of algebra. And a lot of what we do in algebra is about finding the roots of functions. So here is a claim. In algebra, I remember learning that the number of roots, x-intercepts, the graph has is based off of its highest power. So in this case, I have a highest power of 3. Means I should have 3 x-intercepts. I claim I don't. Okay. It's a great claim, but claims require proof. Now, Roll was not necessarily working with the graphical idea. When Roll was working this theorem, he was actually working strictly from an algebraic perspective. He didn't draw pictures to show this. There is a nice formal proof of this idea in our text. But how would I show that this is true? If this is my claim, I should really prove this. I put the word proof in quotes here because this is really just a demonstration. It isn't truly a mathematical proof. Those of you interested in more mathematical proofs should take the course Discrete Mathematics. We do a lot of them there. We talk about the ways in which proofs work. If I want to show there's one and only one of these, first I have to show there's one. Then I have to show there's only one. So let's start with there's one. How do I know there's one? Well, what is f of negative 1? Negative 1 to the third is negative 1, plus another negative 1, plus 1. Well, those cancel, and I get negative 1. What's f of 0? Aha! Why does that aha? Well, when I put in 0, I get 1. I'm looking for roots, and a root is a place where my function is equal to 0. I haven't found an output of 0. But why is this enough to tell me there's going to be an output of 0? There must be somewhere where the output is 0. Dean?
Cross over the x-axis.
I went from a negative value to a positive value, and this function is a polynomial. Polynomials are continuous everywhere. So that's the intermediate value theorem. I went from negative to positive continuously. I had to cross through 0 somewhere. I need to give this x value that we're going to say is our root, I need to give it a name. Let's call it R for root. And what's more, I know that R is between negative 1 and 0. Somewhere between those, I had to cross the x-axis. Beautiful. I have a root. I have 1. But it says up there I have exactly 1. So you need to tell me why you can't have another. Why is this the only one? The problem is I'm not allowed to look at a picture. I have a spot where the output is 0. R. If I had another one, there would be 2 values where the output is 0. Think of the picture we just drew. It scrolled off the top of the screen, but think of the picture we just drew. I have 2 points that are the same height. So now suppose there is another root. What do you want to call this one? I need a name. I used R over there. What do you want to use here? Pick a letter.
W.
I'm going to pick a number W, and that W is not the same as R. Please notice that means that f of R and f of W are equal to each other. Their outputs are the same, but the inputs aren't. Great. Go back and look at Rolle's theorem. What are the three things I need to be able to use Rolle's theorem?
Continuous, differential, and f of a equal f.
Okay, up there on the screen in the paragraph, I see f is a polynomial, f is continuous everywhere. At the bottom of the screen, I see f of a equals f of b if I use R and W as my two values, right? The function is continuous everywhere. So it doesn't matter to me whether R is on the left of W or W is on the left of R. It doesn't matter. It's continuous everywhere. What's the derivative of f? About to run out of room on my screen. What's f prime? Hey, that's a polynomial too, right? And that means that that works everywhere. And if this exists everywhere, then f has a derivative everywhere. Okay, Chase, you just gave me three conditions. And I now have all three of those conditions being true, yes? What's the consequence of Rolle's theorem? By Rolle, the then part of my theorem. What has to happen? Somewhere between R and W. What about the tangent line? Which means that the derivative has to be zero there, right? This is my value C, with f prime of C equals 0. Okay. Do me a favor. Find this C value. You have f prime. Set it equal to 0 and solve. That's f prime of c. I set it equal to 0. What do you get for c? Uh-oh. Can you have something squared be negative? Okay. You just told me if there's a second root, then there's a place where the tangent line is horizontal. The place where the tangent line is horizontal is the square root of a negative number. This is never going to happen in real numbers. So now let me go backwards. Back up these sentences until I see the thing that I assumed. All of this is only going to happen if there's another root. But since this sentence is obviously bullshit, this has to be wrong. So there isn't a second root. There's only one root ever. That was our assumption. And everything we did descended from that assumption. And that dissension led to something that can never happen. This contradiction, if you want this to be true, you get the square root of a negative. Therefore, this thing must not be true. This underlined sentence is the thing that is false. So W can't exist. And f of x has only one root r. There's one. We know what it is. It's r. It's between -1 and 0. And that's the only one. This method of logical analysis is called a proof by contradiction. It is one of the oldest ideas of proving something. It goes all the way back to Greek geometry. Fiona, talk to me.
Only one.
Root R. Yes, that looks like the word route. I didn't close the loop on my other O. I got excited. My handwriting gets worse when I get excited. Now that seems like a really theoretical idea, but it has consequences that Rolle was able to use algebraically to show properties about other functions. Questions? Rolle's theorem is the, quote, simple one. Because Rolle's theorem requires me to have the same output on both ends. A and B have to have exactly the same output. What if they don't? An aside, there is an entire website devoted to teaching undergraduate mathematics with primary sources. And in that case, that means looking at the history of things. I've put a link in our web links section to the history of this result. If you're interested in all in where the hell did this idea come from, this is the place to look at it. There's a lovely paper here. It's only like 4 pages. It's worth downloading. I think it's worth reading if you're at all interested in how did this idea come to be. Let's talk about the more general idea, the mean value theorem. Just like I keep abbreviating the intermediate value theorem, IVT, I'm going to keep abbreviating the mean value theorem, MVT, a lot. So I want you to get used to it at the moment. The best part about the mean value theorem is it starts with the same first 2 assumptions, hypotheses, as Rolle's theorem. Suppose I have a function continuous on the closed interval from A to B, and it's got a derivative everywhere between A and B except maybe at the ends. I'm skipping the third part, just these first 2. Rolle's theorem requires me to say that the ends are equal. So really the idea here is, well, what if the ends aren't equal? How's this going to change our picture? Dean, if I redraw that picture that we drew together at the beginning, I'm going to have an x value A and an x value B. And now I'm going to get 2 different y values. I need an executive decision from somebody. If these 2 values are different, is the one that's on the left, f of A, higher or lower than the one that's on the right? Doesn't matter to me, but I want to draw a picture. You tell me which way I should draw. From low to high or from high to low?
Low to high.
Low to high. So f of A is going to be down here. And f of B is going to be up here. You ready for the sneaky part? I want you to ignore the x and y axis for a minute. Let's take this picture and turn it. What did I just do to the 2 dots? Which means they look like they're the same height. This looks like Rolle's theorem. Only now I have this line between my 2 dots as my quote unquote axis. That's horizontal, isn't it? Now connect at those 2 dots just like we did last time. You can go up and down, you can go down and up, you can go wiggle back and forth several times, you can go straight across on this line, it's up to you, right? But if you connect these dots, what does Rolle's theorem say? No, what's the consequence of Rolle's theorem? The tangent line will be horizontal, right? But in this case, horizontal means matching that line. So I'm going to connect these 2. Last time we went down, then up. I'm going to go up, then down. And I'm going to do it just once. Up and then down. Somewhere in here, I have a point with a quote unquote horizontal tangent line. But that means it matches this line, right? This pencil line. So somewhere up here, right about there, I've got another point. And that point, my tangent line here, is parallel to this line. I'm going to turn the picture back now. Those two lines, except for the fact that I'm a crap artist, those two lines should be parallel. The best part is I can write my conclusion based off of that point. I'm going to call it C again. My conclusion is about C. Then there exists a value x equals C with slope at C being equal to the slope of that line. What is the slope of that line? This line going from f of A to f of B? Say again?
And leave it 0.
But now I've turned it back. So it's not 0, it's not horizontal anymore. Yeah, but how do I figure out what the number is? How do I figure out the slope of that line? And I have the points, right? This point is B f of B, and this point is A f of A. So I have change in Y over change in X. Hey, wait a minute. The definition of that slope, that's our secant line, right? Because it cuts through the graph at 2 points, not 1. That's an average rate of change. I'm going all the way back to the first week of class. That's an average rate of change. What's another word for average? The mean value is the exact value somewhere. When we first talked about derivatives, I said, I get here in 40 minutes. I live 25 miles away. That means I do what? 37 miles an hour. But I don't back out of my garage at 37 miles an hour. And I don't ride the parkway at 37 miles an hour. And I shouldn't be coming up the front drive at 37 miles an hour. But somewhere along the drive, somewhere between the time I start and the time I end, my instantaneous velocity must match my average velocity. The mean value theorem allows me to concretely say it must match somewhere. You will often see this expression rearranged. And so instead of writing f prime of C equals, we'll write f of B minus f of A is f prime of C times B minus A. Change in Y equals slope times change in X. Well, now I can do these same sorts of things with the mean value theorem as opposed to with Rolle's theorem. I can ask, where does this happen? Here is an example. f of x equals x cubed minus x, and I want to look between 0 and 2. So, first question. Whenever I'm going to use a theorem, I have to make sure that I'm allowed to use that theorem. Do I satisfy all of the hypotheses for our theorem? The mean value theorem has two hypotheses. My function needs to be what two things?
You must add, and that is different to what they leave.
So I need it to be continuous over the whole thing and differentiable except maybe at the ends. Is this continuous? What kind of function is this? A polynomial. So f is continuous where? Everywhere. Chase, if it's continuous everywhere, it's definitely continuous between A and B, right? What's f prime? Which is also a polynomial, right? So this exists everywhere. Everywhere I can spell. So f is differentiable everywhere. And that means it's definitely differentiable between 0 and 2. Maybe not at the ends. No, it's even differentiable at the ends, but it only needs to be differentiable in the middle. Hey, I can use the mean value theorem. What does the mean value theorem tell me? Oh, that's this conclusion right here. There's some number C where this holds true. I just need to know what numbers to put on that right-hand side. I need 4 numbers. Aha! F of B minus f of A over B minus A. Take 2, plug it into our original equation. 2 cubed minus 2, that's 8 minus 2, that's 6. Put in 0. 0 cubed minus 0 is 0. Over 2 minus 0. 6 over 2 is 3. Find me the C. Oh, I have my derivative. So let's take f prime of c, 3c squared minus 1, set it equal to this value, and solve for c. I get 3c squared is 4, so c squared is 4/3. That can happen. I just take the square root. And I get plus or minus the square root of 4/3. But I only want one of those. Why? And which one? Because the thing inside the square root can't be negative. The square root could be a negative number, right? Because, right. But in this case, my final answer as C could be a negative number. But I don't want the negative. Why do I know I get to throw out the negative one? No, I get a positive output when I put in a negative value. That's still okay. What is the value of this negative the square root of 4/3? Um, 1.1 something, right? Negative 1.1. Wrong problem. In our problem, I'm looking between 0 and 2. Same idea. I'm looking between 0 and 2. I can't use negative 1.1. I want the number that's in here. I didn't even write that part down when I said what the mean value theorem says. It says there exists a C with this, but that C has to be in our interval. So I really do only have one answer this time. The mean value theorem helps me do things like my linear approximations. Okay. Suppose I have a y value. I know that at 0, my y value is -3. I also know that the derivative is less than or equal to 5 everywhere. Two things to note. If the derivative exists everywhere, the function is differentiable everywhere. If it's differentiable, it's automatically continuous. As soon as I say this sentence, both conditions for the mean value theorem have been made true. Okay, wait a minute. I just said both conditions for the mean value theorem are true, right? that means between 0 and 2, between the x values 0 and 2, my function is continuous and differentiable. The mean value theorem tells me f of b minus f of a is equal to f prime of c times b minus a. Let's use 0 and 2 for f of b and f of a. Sorry, for b and a. So f of 2 minus f of 0 is equal to f prime of c times 2 minus 0. We're asking about the biggest possible value for f of 2. What do I know about f prime of c? It can't be any bigger than 5. Because the whole derivative is never bigger than 5. This thing is less than or equal to 5. And over here, I have f of 2 minus -3. I just have an inequality involving f of 2. F of 2 must be less than or equal to 10 minus 3. If we think of the mean value graph, my derivative is less than 5. So if I draw the line whose slope is 5, I can't ever get bigger than that. So follow that line like our linear approximations. When we step over, we're going to get up to 7. Bounding our function is a useful idea. Two notes. Consequences of the mean value theorem. 1. If my derivative is equal to 0 on every point between a and b, then f of x is a constant on that entire interval. The only way you have a function that has 0 derivative on a section is for that whole section to be perfectly flat. But that's like the consequence of Rolle's theorem, right? The thing has to have a horizontal tangent line. If I generalize this and say that two things have the same derivative on some interval, not that it's 0, but it's the same, then those are parallel. And if they're parallel, that means the difference between them is a constant. I'm usually going to write this f of x is g of x plus c. This one is going to come back to us at the end of this chapter and be an important result. As a matter of fact, it's going to be one of the more important results we have for the rest of the semester. Questions? I look forward to seeing you all tomorrow. And if I believe I check our schedule correctly, what is tomorrow? Yes, but what is it on our schedule? Question and answer day. Because the homework's due Friday. I will see you all then. Have a good day.